For 70 years, there's been one rule in computing that nobody breaks. Analog computers are fast. Digital computers are accurate. You get one or the other, never both. China just published a chip that ignores that rule. And the claim attached to it, 1,000 times the throughput of a modern Nvidia processor, is either the most overhyped number in chip news this year or the first real evidence that analog computing is back from the dead. Today we're going to figure out which one it is. Back before digital computers took over, analog machines were actually the fast ones. Instead of crunching numbers step by step, they used physical quantities, voltage, current, resistance, to represent values directly. Build the right circuit, and the answer wasn't calculated. It just appeared as the electricity settled into place. The problem was reliability. Resistors drift with temperature. Components aren't perfectly identical. Noise creeps in, and the moment your equation gets bigger or more complex, those tiny errors don't stay tiny. They compound, and the instant answer becomes a wrong one. Digital computers won because a transistor being on or off is nearly immune to that kind of drift. You can copy a zero a billion times, and it's still a zero. That's the whole reason your phone, your laptop, and every AI data center on Earth runs on digital logic. So when a paper claims someone built an accurate analog chip, that's not a minor engineering update. That's challenging the premise digital computing was built on. Here's the real project, stripped of marketing language. Researchers at Peking University build a chip that solves matrix equations, the kind of math that shows up constantly in signal processing and machine learning, using resistive memory, or RRAM, instead of a traditional processor. RRAM cells don't just store data. Each one holds a resistance value, and when you push current through a whole array of them, the outputs combine automatically according to basic circuit physics. Ohm's law, Kirchhoff's law. In other words, the array is the calculation. There's no fetch, execute, store cycle. The math happens as the electricity moves. That's the analog computing dream. The team's real achievement is what they did about the accuracy problem. Instead of trusting one analog pass to be correct, they split the job in two. One circuit produces a fast, rough answer. A second circuit, also analog, measures exactly how wrong that rough answer is and feeds the correction back in. Run that loop enough times, and the error shrinks bit by bit until you're sitting at 24-bit precision. Precision that's genuinely comparable to standard FP32 digital math. They tested it on a real workload too. Massive MIMO signal detection, the kind of math cell towers do to untangle overlapping wireless signals from multiple antennas. The analog chip matched digital-level accuracy in as few as 3 correction cycles. That part is real, published, and measured in hardware. Not simulated, not theoretical. Now, the number everyone's clickbaiting with. The researchers didn't run an AI model on an H100 and then run the same model on their chip and clock 1,000 times speed up. That comparison doesn't exist because this chip doesn't run AI models. It solves matrix inversion and linear systems, a narrower, more specific task. What they actually did was model projected throughput. If you scale the array size up, speed up the supporting op-amps, and optimize the surrounding circuitry, their estimate says the architecture could reach roughly 3 orders of magnitude, 1,000 times, more throughput than a leading digital processor doing the same specific task at the same precision. Energy efficiency in that same projection improves by close to 100 times. That's a real number. It's also a projected ceiling, not a benchmark you can point to in production silicon today. And the paper itself admits the advantage shrinks as matrices get larger, because scaling requires breaking the problem into blocks, more steps, more overhead. So, is the number fake? No. Is it the whole story? Also no. Here's the honest version of why this matters. AI training and inference lean heavily on matrix multiplication. That part, this chip doesn't directly accelerate. What it does target, matrix inversion, solving linear systems, shows up in optimization problems, certain scientific computing tasks, signal processing, and some second-order training techniques. It's a specialist, not a replacement. The most realistic future here isn't analog chips replace GPUs. It's a GPU or CPU running the show and occasionally handing off one specific type of equation to an analog coprocessor built exactly for that job. The same way your phone has a dedicated chip, just for camera processing instead of making the main processor do everything. Digital hardware still wins at flexibility, programmability, and general-purpose logic. That's not changing. What's changing is that analog hardware may no longer be too imprecise to trust with real work. This wasn't a finished commercial chip. The full solver still depends on external op-amps, data converters, and a microcontroller sitting alongside the RRAM array, not one clean piece of silicon. Scaling the array bigger brings back the same old analog enemies: noise, wire resistance, manufacturing variation. And someone still has to build the software that knows which equations are even worth sending to hardware like this in the first place. None of that erases the result. It just means solve here means solve in the lab, with a clear engineering roadmap, not solved in shipping. Here's my read on it. The interesting part of this research was never analog is fast. Everyone already knew that. The interesting part is that they stopped trying to make analog perfect and instead built the imperfection into the algorithm itself. Let the first answer be wrong on purpose. Measure exactly how wrong. Correct it. Repeat. That's a different philosophy than the one analog computing has been chasing for 70 years. And it might be the one that finally works. China hasn't built a universal Nvidia killer, but they may have found the missing piece that kept analog computing out of the modern chip era in the first place. And that's a bigger deal than any single benchmark number. So, what do you think? Is this the start of analog making a real comeback in AI hardware, or just a clever lab result that stays in the lab? Let me know in the comments. And if you enjoyed this breakdown and want more deep dives into the future of semiconductors, AI, and cutting-edge technology, make sure to subscribe to Chip Wars and turn on notifications so you never miss a video. Thanks for watching, and I'll see you in the next one.